In this video, we present the Network Digital Twins Demo Proof of Concept demonstration for the 6G-Cloud project. Firstly, let us introduce the NDT building blocks. These are the data repository implemented by Prometheus Time Series database, the NDT engine implemented by Uransom User Equipment and GNodeB Simulator, and the core network NDT implemented by the Open5GS open source core network implementation. The NDT orchestrator is implemented by the NCSR Democritos developed Katana open source manager and network orchestrator. The NDT visualization service is implemented by the Grafana visualization solution. Our demo setup consists of physical network, Amorosoft Classic, RAND and Core, two 5G UEs, networking digital twin, Open5GS Core, Uransom, virtualized UEs, GNB, NDT orchestration, Katana, traffic generators, IXIA chariot, computing infrastructure, Proxmox VE cluster. The workflow for the demo consists of 5 steps. In the first step, we deploy the physical network. In the second step, we use the NDT orchestrator to deploy the network digital twin. In the third step, we run similar traffic scenarios in both networks. In step 4, we gather the real-time telemetry data in both networks. Finally, in step 5, we evaluate the NDT performance in relation to the physical network. The first phase of the deployment process involves the initiation of the physical network, during which physical network services are activated and the user equipment attachment procedure is carried out. The process consists of several key substeps that ensure successful registration, authentication, and signaling exchange within the network, namely non-access stratum registration and authentication messages. In step 2, the network digital twin deployment process is executed using the Katana management and orchestrator. In this phase, the Open5GS network service descriptor and Kubernetes network function are uploaded to open source Mano. In the next phase, the Open5GS is deployed using Katana, ensuring that the correct service instances and network functions are instantiated within the Kubernetes environment. In the next step, we initiate the NDT deployment. During the initiation and session establishment phase, signaling messages between different components of the 5G network are exchanged, ensuring session establishment. Namely, AMF connectivity messages, RAN network and GAP/RRC registration messages, and UE session establishment messages are successfully exchanged. Out testing scenario includes 2 UE nodes for both the physical network and its NDT counterpart. Similar traffic is run in both the physical network and its network digital twin. Each UE runs different traffic mixes. Each UE has a different QoS SLA. UE1, 17 megabits per second, and UE2, 10 megabits per second. The validation procedure includes the successful deployment of the NDT and its ability to generate identical data logs and performance metrics with the physical network. Physical network testing and evaluation. At the top half part of the video, the traffic flow scenario running from the IXIA chariot network performance testing tool is shown. TCP uplink traffic is generated from each UE towards the IXIA chariot server. At the bottom part of the video, we see the Amorosoft physical network web interface, where the uplink traffic flows are presented. We observe the uplink traffic throughput of UE1, represented by the red line at 17 megabits per second, and the uplink traffic throughput of UE2, represented by the green line at 10 megabits per second. Total throughput is represented by the blue line at 27 megabits per second. For the deployed network digital twin, we run the exact same scenarios as performed in the physical network. As shown from the Grafana dashboard, TCP uplink traffic is generated from each UE towards a server interconnected with the NDT. At the left part of the dashboard, from top to bottom, we measure the UE1 and UE2 uplink throughput, the total throughput at the UPF interface, OGSTUN, and the memory usage of the VM. At the right part of the dashboard, we measure respectively the total network traffic VM throughput, the VM CPU usage, and the packet loss from the UPF interface. By focusing at the -UE1/UE2 and -OGSTUN, we observe the following. The uplink traffic throughput of UE1 is represented by the green line at 17 megabits per second. The uplink traffic throughput of UE2 is represented by the yellow line at 10 megabits per second. The total throughput is 27 megabits per second. We conclude that the NDT has a similar performance related to the physical network as tested. Analyzing the results, we conclude that the NDT network is successfully deployed, producing similar performance results with the physical network, and that our methodology provides an expandable NDT creation methodology. Our next steps include, firstly, the extended implementation of the proposed methodology including multiple UEs, diverse traffic mixes, and network topologies. Secondly, the support of the 6G Cloud AI/ML framework for model training and performance optimization.